So the next gemstone we're going to talk about is actually a mineral, beryl, which you may or may not have heard of. Beryl is an interesting mineral. It's an aluminosilicate, so you can see here beryllium, aluminum, silica, oxygen. Some of the pretty common players in the geology world. And this is a mineral that generally occurs in pegmatites in kind of cooling igneous rocks. So hopefully you remember learning about pegmatites so long ago. So when beryl grows in its crystal form in these kind of pegmatite environments, it oftentimes forms these kind of hexagonal columns almost, with no cleavage, but it gives it a pretty unique shape. And so beryl, this kind of regular old beryl, is something you can buy at a rock shop. You know, it kind of looks cool and it's not incredibly uncommon, but there can be some really interesting things that happen within the crystal lattice to make kind of regular old beryl what we would call gem quality beryl. So if beryl's included, meaning that's the inclusion or the impurity with iron, so iron 2+ or 3+, again, for those following chemistry out there, it actually forms this mineral called aquamarine, which is kind of this really cool, almost like Caribbean seawater blue. And it occurs in a couple of locations worldwide. It's not incredibly common, but it's not super rare. Notably, one of the places where aquamarine is kind of abundantly occurs is actually in the Sawtooth Mountains outside of Stanley, Idaho. Although it's a national recreation area, right, the Sawtooth NRA, so you can't go collect there. I'm sure people do. But definitely, I've never been up there myself, but I've had colleagues who've gone up and kind of appreciated the aquamarine crystals in the Sawtooth batholith. So a slightly more common impurity, chromium and vanadium, again up to about 2% chromium, I think, that produces what we know of as an emerald, right? So emerald and aquamarine, as you can think about gems, you know, visiting the Emerald City or something like that, they're just different versions, or they're essentially kind of the way that these impurities show up in the mineral beryl. So there's even more. We can kind of do a quick rundown of some of the other things. Again, aquamarine and emerald being the primary, but there's also something that we call a golden emerald or golden beryl. Pink beryl can occur with magnesium impurities, which is pretty interesting. With a slightly different type of magnesium, if you have magnesium 3+, we can actually get these kind of deep red emeralds. And again, those last ones are a little bit kind of less common, but still definitely in the range of what we would call precious stones, right? So again, there's kind of weird versions of emeralds which are pretty sought after. The next mineral that makes a showing in our precious gems is corundum, aluminum oxide, which is not a silicate mineral, which means that this mineral kind of forms under different conditions. Generally it forms under metamorphic environments as you know, pressures kind of driving certain elements or certain molecules to react with one another. Interestingly, corundum has a crystal form or crystal structure that's very similar to beryl, we saw in the last discussion, although corundum isn't quite as varied as beryl, but it really has two kind of well-known impurities that produce gem quality corundum. So when corundum is included with chromium, so again as a parts per million kind of impurity in the crystal lattice, it actually produces this very deep, kind of beautiful, almost like pinkish red, almost magenta color that we know as a ruby, right? So a ruby is essentially just chromium included into aluminum oxide. More wiggle room with the kind of next gem here. Transition metals included in our aluminum oxide actually will produce this really cool and invariably blue version of corundum known as sapphire. And because you can imagine the transition metals, that's 40 or 50 different elements of the periodic table. I don't have one to look at right off the top of my head. So sapphires themselves can be pretty variable, but they do have this really kind of deep, like haunting blue, right? Remember that was something I said in the beginning of this intro, is that there is just something kind of aesthetically pleasing about these, just kind of beauty for beauty's sake, and I think sapphire is a really good example of that. Pearl. So I know this is not a traditional geology class. One of the things that we learn about in a traditional geology class, like physical geology, is that there are kind of 5 qualifications for something to be considered a mineral. It has to be solid at Earth's surface temperatures, it has to have a defined crystalline structure, chemical composition, naturally occurring, and inorganic. So biology plays a significant role in the formation of pearls. The material itself is oftentimes inorganic, but it's secreted by an oyster or a mollusk. So again, it kind of fuzzes the balance there. But, that aside, the formation of a pearl has to do with these guys, mollusks. In particular, a pearl oyster, right? So there's kind of one type of mollusk that makes a pearl that we consider gem quality. Almost all mollusks will make something that meets the technical definition of a pearl, but is nearly worthless. Sometimes they call them kind of calcium carbonate concretions. But to start our story, one of the things that happens here is, I'm not a kind of biologist by any means, marine biologist in particular, but an oyster or mollusk in general will secrete this material to coat the inside of its shell. And that material we actually call mother of pearl. So mother of pearl is pearl-esque material, but it's kind of spread in thin layers along the inside of a shell. Well, this is also true for pearls. The thickness of the individual layers that the organism is secreting, the thinner they are, the more kind of iridescent and almost metallic it starts to look. You've probably seen an abalone shell, right? They have this kind of cool, rainbowy, iridescent inside. So that material is mother of pearl. It's not kind of a pearl itself. The rest of the story is then the oyster kind of using this ability to secrete this material focused on some sort of irritant. And again, you've probably heard about this, or at least kind of thought. So here, if we have a grain of sand or a little bit of shell, it slowly begins to cover it with mother of pearl. And over time, that develops these kind of concentric rings, and we get kind of a traditional pearl. Now, the kind of process that I've outlined here, that's for a natural pearl. And it turns out, of naturally occurring pearls, the idea where you just go into the ocean and this has kind of happened by chance, it doesn't really happen in the kind of volumes that would make there be a pearl industry, right? It's actually pretty rare. Here in this image, you can see this is actually an SEM image of the cross-section of a pearl. And you can see those little layers of a mineral that you've actually heard of before. Depending on how we classify minerals, a pearl is actually made out of calcite. The same thing the limestone is made out of. But it's made out of a particular type of calcite known as aragonite. So then that's kind of where we get into the weird definitions of a mineral. Again, it doesn't occur naturally very often. Generally what we do is we culture pearls. And so we can take a couple of different things. Usually we would take some sort of artificial irritant, right? Like an artificial sand grain. Oftentimes they use some sort of bead. So I'm going to erase my pearl here. And we could surgically implant this, and we could actually do a couple of them. So we could implant these beads, again, surgically. Open the oyster carefully, do a little oyster surgery, stick these beads in there. There's a couple of different types of material that we use for these beads. But the process kind of after that remains the same. And so you can then take the pearl, or take the oyster, the pearl oyster, kind of very specific species that does this kind of a way that makes their material prized and kind of gem quality. And we can take that guy, put it back in its environment, whether that's freshwater, which does exist, right? There are freshwater oysters, and then also marine. So they do a lot of this work in Japan and China. And And then the oyster goes to work and it finds this irritant, in this case, a couple of them, and it starts coating them with these aragonite layers. So maybe in as little as 18 months or, sometimes just kind of 2 years, we can take that oyster out of its environment. Then oftentimes we can kind of reseed that same oyster, put it back down in the ocean, and it will produce more pearls. So, in any one oyster, you can now get multiple pearls, but those pearls are chemically a little bit different because, again, they have this fairly large nucleus, right? The bead that was implanted, and then that is covered with true aragonite, or true kind of mother of pearl. So if you were to compare a natural pearl with a cultured pearl, visually you wouldn't be able to tell the difference, right? So kind of as you're holding them in the hand, you're looking at the exact same material on the surface. So they are truly pearls. But once you do some X-ray analysis, it's pretty obvious. Because we can do this relatively easily, we've kind of figured out the techniques that make this work effectively. The pearl market is almost all what we consider cultured pearls. I mean, if you can find a certified, look at the X-ray certified natural pearl, that's going to be much, much, much more valuable than a cultured pearl, although nobody's going to be able to tell the difference, right? Because on the outside, they're identical. So the ideal pearl is round. And then I had mentioned how, depending on how quickly that organism is laying the layers of aragonite or calcite, so the thickness of the layers, if they're really thin, it tends to appear kind of iridescent, and as they get even thinner, it almost starts to look metallic, whereas kind of typical pearl is this kind of pearlescent or kind of opalescent round sphere. There's also pearls that have grown naturally that are really strange shapes, right? So maybe the irritant was kind of a different shape, or you could even do this artificially, seed or a bead, like to start the pearl, that's a different shape, that's elongate like a grain of rice or something. And so you can make pearls that are strange shapes. But again, those occur, you can make them artificially in the cultured pearl world, or you could find those naturally occurring.